Advanced Algebra 2 students, these are your 9.5 notes. Today we're going to look at the fourth and final conic that we're going to study, the hyperbola. So again, we've seen circle, we've seen parabola, we've seen ellipse, now hyperbola. First of all, the definition of a hyperbola is the set of all points in a plane where the difference of whose distances from two distinct fixed points, called the foci, is a positive constant. I find that definition a little bit difficult to grasp at times, but what we're talking about when you see these D1 and D2 values, the difference between them is constant. Again, kind of hard to grasp that, but we're going to show you some ways to graph without having to worry too much about that particular definition. Now, if you look at the next diagram, you'll see we've got several things labeled. We've got an A value, we've got a B value, we've got a center, vertices. The transverse axis is important. That's the axis that connects the foci together. And then each side of the hyperbola is called a branch. All that stuff will come into play. It is important to consider there is a B value on here as well that we will use. You just don't see it on this particular diagram. The other thing that's kind of next to that is the asymptotes of a hyperbola. I'm going to suggest to you that you don't need to spend a lot of time memorizing that formula. If you follow the graphing techniques that I use today, you'll be able to figure out the equations of the asymptotes without having to memorize anything. Just simply look at it and you'll see the equation for those lines. We're going to use your old friend point slope on that one. Okay, so again, lots of little details. We'll work through those as we move ahead. Now, as we scroll down here, you can see we have standard forms. We have a horizontal standard form and a vertical standard form. When you analyze those, you quickly realize some similarities, like they're both subtraction. Both of them have a squared first and then b squared to follow. But here's the big difference. The horizontals, like the two that we have up above, have an x minus y situation, where the vertical have y minus x. I should probably point out here too that A isn't always bigger than B. It can be smaller, it can be bigger, it can even be the same as B. But it's different from ellipses in that A was always the biggest in an ellipse. That is not the case with hyperbolas. C is always going to be the largest of the three. Okay, and so I'm again highlighting the fact that it's a subtraction situation. Hey, one other thing you notice on the right, you see how it says c squared equals a squared plus b squared? That is the relationship between sides A, B, and C. It's the relationship you have grown to love and to know, the Pythagorean theorem. It's none of that silliness that we saw on the ellipses. So again, you need to recognize these forms, know which is horizontal, which is vertical. But when we get through the graphing side of this, some of the techniques we use will help you to keep that information straight. Okay, so on number one, we need to find the center, the vertices, the foci, and the asymptote equations for the hyperbola, and then we'll sketch the graph. So the first thing I notice, in a similar fashion to what we had on ellipses, we can pick out the center very quickly. We can see that there's no movement from the origin, so it's still at the origin. Also pretty quick to pick out would be the A and B values. Remember, A is always first, so a squared is 9. That means A is 3. B would be 4. And then we know the relationship is the whole Pythagorean situation. A squared plus B squared equals C squared. That's your nice, simple Pythagorean triple. So C is 5. Okay, at this point, what I typically do is start marking down some of the key stuff. So I've marked the center of this graph to be right on the origin, and then I'm looking at the A value, and I see that the A value is 3, and I also see it's connected to X. When I see it's connected to X, that reminds me it's going to be horizontal, so I need to mark a point 3 right and 3 left. By the same token, I see that the B value of 4 is connected to the vertical variable y. So therefore I'm going to mark a point up 4 and down 4 from my center. Now here's something we do is a little goofy, but it really helps us with our sketches. We draw a rectangle. Again, this rectangle is not actually part of the graph. It's just a guide. That's why I'm drawing it dashed and why you should do the same thing. But it's very, very helpful. It tells us a few things. One, it kind of helps us to see where the vertices are. If I and I'm marking the vertices in red now, but the vertices, I know that they're on the left and right because this thing is x minus y. It has to be horizontal. Here's another thing. If you draw the diagonals of these rectangles and extend them, both directions, these are the asymptotes for the graph. Okay, so this is pretty cool stuff. You've got your asymptotes, you've got your vertices, and so honestly at this point all you really have to do is start at the vertex on either side and draw either side of your hyperbola like you see I'm doing here. And there it is. There's the hyperbola. Now there's one thing I haven't marked just yet. The foci, we'll put those on there as well. So I see that the foci come from the C value. The C value is 5, and they're always going to be the same direction. So since this hyperbola opens horizontally, I know the focus points are inside the hyperbola, 5 units from the center. Okay, we let's mark it all down. The vertices, we went 3 spaces left and right from the center, so we can just write those as plus or minus 3 and 0. The foci, we did similar thing where we started at the center, but then we went left and right 5 spaces, and we can mark those plus or minus 5 and 0. Okay, the last thing we're going to look at is the equation for the asymptotes. Now you can see there are these just 2 lines, but here's what's great about these 2 lines. The slopes are opposites from each other. So, and they share that point, that center point. So we can use our old friend point slope, and we can just write y minus 0 equals, and then we find the slope, and if I look over there, I can count. It's 4 and 3, 4/3, or the other line's negative 4/3, and then times x minus 0, or just simply plus or minus 4/3 x. And we're done. Let's do another one. Very similar question in some ways. This one will be vertical. I can see that right away because it's y minus x, but the center is still at the origin. Once you kind of get that, then we'd want to go ahead and find those a and b values. This time they're 5 and 1. By using that Pythagorean relationship, we know c would have to be the square root of 5 squared plus 1 squared, or just simply square root of 26. Once you get here, it's really not too big of a deal to go ahead and draw your center and then start sketching your box, or your rectangle I should probably say. Now this rectangle is a little funny because it's so narrow and tall, so a little different than some of the others, but that's fine. It works the same way. So again, go ahead and use the dash lines and draw the box, the rectangle that connects those 4 points, and then we use the diagonals from that rectangle allow us to have the asymptotes for our graph. I'm just getting those extended in all 4 directions here. Now again, remember this particular hyperbola is vertical, so I know that this hyperbola is going to open up and down, so I'm going to sketch using the vertices on the y-axis. Basically, it's going down and going up. Like you see here. All right, we still haven't mentioned the foci, but we found the c value was square root of 26. If you think about square root of 26, it's just a smidge more than 5. We're not going to worry too much about precision here. It's going to be real tough to be able to tell the difference between square root of 26 and 5.5 or something like that. So we're just going to approximate it. We will label it down below though. So first of all, here are the vertices. We know those are going to be up and down 5 spaces from the center. So we'll just do 0 plus or minus 5. And the foci are up and down square root of 26 spaces from the center. So 0 plus or minus square root of 26. Last thing we need to do here is we need to go ahead and write the equation for the asymptotes. We're going to follow the same format. Y minus 0 equals. Now we'll find the slope. In this case, the slope of those lines is either 5 or negative 5. So we'll do plus or minus 5. And again, it's x minus 0. So we can just do plus or minus 5x in this case. And there it is, a vertical hyperbola. Pretty cool stuff. And now for number 3, you might notice right away on this one that we have a couple of little things to deal with that we haven't had to deal with yet. One of those being that the center has now moved away from the origin. Finally, center is -1 and 2. All right, no big deal there. Here's what you may not love so much, the fractions. So what's going on here is our a value and b value have to be the square root of 1/4, square root of 1/16. I've got those values. And I might as well go ahead and find c while I'm at it. I know I don't have to label the foci immediately, but might as well go ahead and get them. All right, so here we go. This is 1/4, this is 1/16. Add those together, you get 5/16. So c would be the square root of 5 divided by 4. Now, I have the advantage of kind of looking ahead on this problem, and so I know that I really want to change the scale on this graph. Instead of counting by ones like we typically do, I'm actually going to count every 4 spaces counts as 1. Now you might be able to look at our values and figure out what made me decide to do 4 spaces. The biggest reason would be, well, first of all, we have small numbers for the center, -1 and 2, so I know I didn't have to move too far. But the other issue was the b value being 1/4. If I make every space worth 1/4, that makes it much easier to go ahead and draw that rectangle in the middle. So here we go. Our center is at -1 and 2, which would put me right about there. And let's see, our a value is 1/2. That means I'm going to need to move in the vertical direction half a space up, half a space down. And horizontally, our b value is 1/4, so I'm going to move 1 space each direction. And you might already be thinking about this. We are going to be going off our grid just a little bit with the hyperbola. I still think it's better to go ahead and stretch this thing out a little bit rather than trying to draw some super duper tiny hyperbola that fits, but we can't really do anything accurate with it. So I'm jumping ahead and drawing the asymptotes that we're going to be using here. And need to stretch those the other direction as well, right into the words for the problem. That's all right. And we kind of know as well the direction, since it's y squared minus x squared, it's vertical. So I know the hyperbola is going to look something like this and this. Okay, other things I know. We found that the foci was square root of 5/4 was the c value. So the foci would be just, square root of 5 is just a little more than 2. And so 2 divided by 4 is 1/2. It's a little more than 1/2. I'm not going to worry too much about trying to be precise on these because, again, I'm not sure you're going to be able to tell the difference between 2.27 and 2.35 and 2.5. We're approximating this whole thing. So, all right, we've listed the center. Let's talk vertices. From the center, we would move, of course, up or down a half a space. Those are our vertices. The foci, also moving up or down, but by square root of 5/4. And then our equation for the asymptotes. This is where the whole point slope form thing really can come in handy. And so I'm going to write it like this. I'm going to do y minus 2 equals, now our slope, I know that each of these spaces count for quarters, not for ones, but truthfully our slope is still up to, right, 1. Our slope is 2. So it's plus or minus 2 times the quantity x plus 1. Now, some teachers might prefer that you go ahead and move that 2 to the other side and make it 2 plus or minus 2 times x plus 1, something like that. For me personally, I'm okay with either of those forms, but talk to your teacher to make sure they aren't picky about something like that. All right, and I think we've covered that one. Let's continue on. All right, up next, we're going to look at some clue problems. Now, my advice to you on a clue problem is, unless you're 100% accurate, do yourself a favor and do a quick sketch and just try to remind yourself what it would look like. Vertices are at plus or minus 4 and 0. The reason I'm doing this is by just simply knowing the vertices, it reminds me which way this hyperbola opens. That's really helpful. Okay, now the center is at the origin, they say, which I could have actually figured that out based on the vertices or the foci. But the other thing I need to know is I need to figure out that b value. I know a is 4, I know c is 6, so 4 squared plus b squared would be 6 squared. So b squared is going to be 20, 36 minus 16, and actually when we think about standard form, I'm going to be all right just to know b squared. So it's x squared over something minus y squared over something. Let's make sure you understand where that's coming from. I know x is first because it's horizontal. I know it's minus because it's a hyperbola, not an ellipse. And the other part I know is the center is at the origin, so these are just x and y squareds. It's always equal to 1. A is always going to be first, and by a I mean a squared, and then b squared is always second, and we have ourselves a lovely equation. All right, here's your next one. The foci this time it says are at 0 plus or minus 5. So again, I think it's smart just to do a quick sketch, just to remind yourself, if the foci are at 0 plus or minus 5, that means this thing has to open around those two foci, so it's essentially opening up and down, it's vertical. Just something to keep in mind. All right, also knowing that the foci are 0 plus or minus 5 tells me that the c value is 5. They gave us the center being at the origin. Now the asymptotes being plus or minus 2 is a little bit interesting on this one, okay? We're going to have to figure out, is this an a over b or a b over a situation? In other words, when I jump ahead here, I know it's going to be x squared or y squared. And in this case, we know it's going to be, actually, I'm going to just write this up here. We know it's going to be y squared over a squared minus x squared over b squared equals 1. We know this because it's vertical, right? So I know my slope has to be a over b. So I know a over b has to equal 2. That's the slope of the asymptotes. So what I'm going to do, and this is a little interesting, but I'm just going to multiply both sides by b, so I'm going to know a equals 2b. And when I do my Pythagorean, it's going to be a squared, but we know a is 2b, or not 2b. That's, never mind. I can't resist that. Yeah, sorry, dad jokes win the day. All right, so 4b squared plus b squared is equal to 5 squared. So this is going to be 5b squared equals 25. B squared is going to equal 5. Now, again, we remember that, hey, if you know b squared, that's really all you need for the standard form, but there's an issue here. We also have to figure out a. So I'm going to do this. B is equal to the square root of 5. That tells me that a is 2 times the square root of 5. All right, and perhaps more important, a squared, if you square that, that's 4 times 5, so that's square root of 20. Oh, not square root of 20. Apologies, just simply 20 is a squared. All right, that number is going to be important to us because that's the one that we're going to plug in right under our y value. Y squared over 20 minus x squared over 5 equals 1. A little bit going on there. That's a little more challenging when you get the equation for the asymptotes rather than directly an a, b, or c value.